Good day, guys. So today I'm going to be talking about strain energy. Strain energy. So first of all, we need to define what strain energy is. Strain energy is the energy possessed by a body when it is stretched within its elastic limit. So in this case, we are seeing the energy due to straining. Now, this is gotten by plotting a graph, a straight line graph, where we have this as the load versus the extension. So this symbol is this from our last video. So we are plotting a graph where we have the load versus the. So now it is very simple. The area of this graph is going to be the work done due to straining, or the energy due to straining. So this is a right angle triangle. We know that the area for this, the area of a right angle triangle. So we have the area of a right angled triangle. So we have the area to be what? Half base times height. So this, we know that this is the area of this right angle triangle. But in this case, if we are to calculate the area, in this case, we say that the area, the work done due to straining is equal to what? The area of the right angle triangle. So we have the area of the right angle triangle. Let's give it like this. So now it's very understandable that we know this expression from mathematics, but we don't have our terms in terms of B and H. We can see where the vertical is represented with what we call the height. So from here to here will be represented as B for the right angle triangle, while the base will be presented as what? The extension. So if we know that the work done by straining, which is presented by U, is equals to what? Half base. We say the base is going to represent the extension multiplied by what? The load. Very understandable. So now this is the formula for the strain energy in relation to what? The right angle triangle formula area. So now from our last video, we said that the stress is equals to the load over the area. So let's make the load subject formula. So we have this is the stress multiplied by the area. We also know that Young modulus, but we also know that strain is equals to what? Extension over what? Original length. Let's make extension subject formula. So we have extension is what? Strain multiplied by what? The length. So very good. So let's substitute these values into this. So anywhere you see this, you substitute as this. Anywhere you see your load, you substitute as stress multiplied by the area. So our strain energy is equals to half multiplied by, now we're having this, so we're going to express this as what? The strain, the length, multiplied by what? The stress and the area. Okay, let's continue. Okay, so now we have this expression. So let's simplify this. We're having the stress multiplied by area multiplied by length over the strain over what? 2. Now everything is expressed in terms of the stress, the area, the length, and the strain, but we don't want a relationship in terms of strain. So which formula can we represent and substitute the value of strain into here? Now from Young modulus, we say that E is equals to what? From Young modulus, we say that the E is equals to the stress over the strain. Let's mix the strain subject formula here. So we're having the strain is equals to the stress over what? Young modulus. Very important. So now let's substitute the value of this strain into this equation here. So we are having the stress, the area, the length all over 2 multiplied by the stress over what? This value here. You can see that this stress multiplied this stress is going to have that the strain energy is equals to what? The stress square, the area, the length, all over 2E. Very, very important. So take note, this is the formula for what? Our strain energy. Now take note, we are having area multiplied by length. We know that volume is equals to area times length. So we can change this expression as what? The stress square volume over 2E. This is another expression for what? The strain energy. So let's go to sample problems involving stress, strain,